So let's say you're stacking pebbles on the beach, and for each column you stack one more pebble than you did the previous one. And you want to find the sum of all these pebbles. So 1 plus 2 plus 3 plus 4. We are trying to find the sum of n. So you stack pebbles in the same manner, and you build another stack next to it, just like that. And then you rotate this stack, and you put it next to your original, just like that. So you notice you stack it up. Your first stack was n units long. 1, 2, 3, 4. We used 4. And it's just as high as it is long. But now notice this is n plus 1 here in the width. And you are actually able to divide this into to get your original stack of 4 long and 4 high triangle, where we can find the sum if we do multiply n plus 1 times n to get the area of this square, and then we divide that by 2. That'll be the number of pebbles we originally were stacking up. Okay, so we found this out with pebbles, but how can we prove it using a rigorous mathematical proof? And that proof would be induction. So we want to start with the base case of, and we'll say n equals 1, and just prove that it's true for that. So in this case, it would be 1 equals, and we're using n equals 1, so that's 1 times 1 plus 1 divided by 2. So 2 times 1 divided by 2 equals 1. Yes, the base case is true. And now we go on to the induction step. And this is, we will assume that this is true for n equals k, and we want to show that this is true for n equals k plus 1. So we want to find the value for, or test the sum for any arbitrary value of k. So because of our assumption step, we're going to assume that this is true for k. So we have k times k plus 1 divided by 2 plus k plus 1, that's our next column, is the k plus 1 column, and this is all the previous columns that we've already assumed are true. And this, we are testing to see if this is equal to our final value, k plus 1 multiplied by k plus 1 plus 1 divided by 2. And if this is true, we will have proved through induction that this is true. So you notice that kind of this term, our formula, which we kind of found out by pebbles, but that's not rigorous, so we're using induction to make it rigorous. We found that this formula is on both sides of the equation. On the left-hand side, it's in the form just as k is k. And we assume that n equals k, this is true. So we're able to say that for all of these, we assume that we can just substitute that, because this would really be 1 plus 2 plus 3 plus 4, all this. We're going to substitute all of this just as this. We're going to assume that's true. And then we're going to add the final value, which is k plus 1. Okay, and on the right-hand side, we just have this formula, but instead of writing k, like we did here, we put k plus 1, and we wrapped all those up in parentheses. So this is on both left and right-hand side, and the difference is on the right-hand side it's k plus 1, on the left-hand side it's just k. So let's go back here and just verify, see if these are true. All right. So on the left-hand side we have k squared over 2 plus k over 2 plus k plus 1 equals, and we're going to simplify this right here as just k plus 2. So we have, we'll FOIL it out here, k squared 2k plus 1k 3k plus 2, and this is all over 2. And you're seeing pretty soon here this is equal to each other. And so that's how you do basic induction for a Gaussian sum, and then you can use it. I mean, if you set a series equal to something, you're able to use induction to either prove or disprove it.